If you want to pick up a key packet, you can. I think the best way to work with a general term is start with whatever they give you and then just keep adapting it and changing it into the new general term that we need. We take our initial general term, replace our x with x over 3. We can also do that with our general term as well. And then distribute the x through, do that with a polynomial first 4 terms and distribute through. As well. So when that x gets distributed through, you're having to multiply x with x to the n. So that's really x to the n plus 1. And then I just distribute the exponent through so I can just get it a little bit cleaned up. So that I'm not having to do a complex fraction. But I think even if you did a complex fraction, I don't think it's a big deal. This looks a little bit cleaner. But I think any of those variations. Take part B. Determine the interval of convergence for the series, for Maclaurin series F. So we can just take the general term and then do our ratio test with that. And then after you find your potential interval conversions, then you're going to test the endpoints as well.
You answered this question a few days ago, I think, but like, why don't you use the alternator when you're doing ratio tests again?
Because here's ratio test. Ratio test has an absolute value bar around it. So it's going to force any alternator to be positive. So we can just basically. So once we can get that cleaned up, we can get it into that x minus c is less than r. We know 3 is your radius of convergence. Your center is at 0. We can build your potential interval convergence, and then you test your endpoints. One endpoint is going to diverge by nth term test. The other endpoint will converge by an AST.
Why don't you consider the alternator when you're testing for x equals -3? Like, why do you just remove it altogether instead of like looking at it as an alternating series? Or is -1 and +1 not an alternator?
Oh, you mean right?
On -3.
Oh, okay, -3. The reason why is because they're both -1. Well, they're both raised to the n+1. So we're following this rule here that says if I have a to the n times b to the n, that's the same thing as ab to the n. So if I do -1 times -3, it becomes +3. +3 to the n+1 is just going to be always positive.
Okay.
So now there's no alternative there. Okay, part C. Let P sub 4 of x be a fourth degree Taylor polynomial for f about x equals 0. Use the alternating series error bound. So that's nice. We don't have to decide whether it's AST or Lagrange. They're telling us. And whenever we see that absolute value, we know that difference between the polynomial and the actual function. We know we're looking for an error bound. And we know that if we want to approximate how accurate our fourth degree Taylor polynomial is, we can just use the first unused term. In this case, the first unused term is going to be the next degree up, right? Be x to the 5th over 5. Just in this case, it is increasing consecutively, so we know the next term will be with that x to the 5th over 5. I put part C up here. I was running out of room, so I put C up here. Okay, any questions with page 32? Let's go to page 43. Okay, so this, I believe was a shared, ABBC problem. Right, so this one, kind of gave students a bit of trouble because, a little, it's kind of hard to see what we're trying to use here. But it says the inside of a funnel of height 10 inches has a circular cross section. So that means if we're to slice it, you open it up, you're gonna get a circle, so circular cross section. So that's a bit of a hint here. As height h, at height h, the radius of the funnel is given by r is equal to 1/20th 3 plus h squared, where h is between 0 and 10. Units of r and h are in inches. Find the average value of the radius of the funnel. So part A is not too bad, right? Average value, we can rely on average value theorem. So start off there. This is non-calculator. So let's see if we can set that up. Your h is your independent variable and your r is your dependent variable here. So treat h as your x. So we do have to set everything up by hand. No calculator. We have to rely on power rule to find our antiderivatives, distribute the 1/10 through, and then evaluate between upper and lower bound. You can leave your answer unsimplified. So that's the benefit of non-calculator. This is just as good as the final answer. You can leave your answer unsimplified. Any of those variations are fine. Okay, any questions with part A? Pretty straightforward so far. Okay, part B, find the volume of the funnel. So the hint is that there's a circular cross section here. So any idea what's our strategy here if we're trying to find the volume and we have circular cross sections involved? So when we do cross sections of other shapes, right? Either triangle or rectangle or semicircle, we have that cross section formula. But what about the other volume formulas that we've learned? What about disk and washer method? Those have what? What cross sections do they have? Circular cross sections. So the strategy, what they're trying to get us to use is they're trying to get us to use either disk or washer method. But it takes a little bit of kind of thinking outside the box because this is not X and Y axis. And so we kind of need to think of this as, what if we were to turn this on its side and then just thinking of it as this curve here, and then rotating that curve around the y-axis, and then that will create this method, right? That's tough. That's a really tough one. I think some students after this year's test, some students were saying that they were trying to do volume of a cone, and they're doing similar triangles, but this isn't quite a cone, right? That curved is not quite a cone. So similar triangles, cone doesn't work. So we really have to kind of think of it as flipping it on its side, thinking of this curve as y is equal to 1/20th 3 plus x squared, or in this case, r is equal to 1/20th 3 plus h squared, and you're taking that curve, rotating it around the h-axis or the x-axis, and then that is going to create that funnel shape after that rotation. It's a tough one. But if we can see it from this perspective, then we know our radius is just going to be top minus bottom. All we need is one big radius. There's no gap. There's no hole. And then we just set it up, find our big R, our big radius. And then B equals pi big R squared from 0 to 10. So we're treating our H as our x-axis, and then our y-axis is our R. And again, we do have to work all this out by hand. We wouldn't want to go through use substitution because this is manageable. We can FOIL all this out. This is just degree 2, so that's what we should do. We should FOIL all this out, expand everything out, rely on power rule, then plug in upper and lower bound. Again, I know it's messy without a calculator, but take advantage of what they allow you to do with non-calculator is you can leave all your answer in one big mess. Don't try to spend all this time trying to do common denominator and cleaning it up. This is good enough. Oh, and then I need to attach pi at the end too. Oh, you got everything? You're good then. Thank you. Part C. Everybody okay with part B? Part C says the funnel contains liquid draining from the bottom. At the instant when the height of the liquid is height of the liquid is 3 inches. The radius of the surface is decreasing by a rate of 1/5 inch per second. At this instant, when the rate of change, what is the rate of change of height with respect to time? So anytime we see those keywords there with respect to time, we should be able to connect with, okay, maybe they're trying to get us to involve related rates. So keep reminding ourselves that, you're probably not going to see a full related rates FRQ, but you're almost guaranteed to see some application of related rates somewhere in one of your 6 FRQs. So be on the lookout for that. So we're basically going to be taking this equation and we're going to find our DRDT. We're going to produce our DHDT. So we're going to just rely on power rule to find our derivatives, but then your DRDT and DHDT will show up each of the derivatives that you take for the variables. Okay. And then you're just gathering all that data and then plugging in with the information that's provided in the problem. So R becomes DRDT. The 3/20th will go to 0. The 1/20th h squared will become 1/20th times 2h times DHDT. And then we just take all this information that they give us, plug in, and solve for DHDT. Yeah, I think the challenge for FRQs is, can you figure out the first step? If you can figure out the first step, everything kind of just falls into place. Or at least it gives you the ability to maybe earn some points. So just being able to, identify your first step is really big for all these problems. All right, a few minutes here. Let's just see if we can try a little bit of page 44, just another Taylor series one here. So they give you the order pair, they give you the slope. you can find the second and third derivative using their formula. And then you can put it into build out your first four terms. And then your general term is basically the formula they give you divided by n factorial times x minus 1 to the n, right? You're just having to replace this numerator portion with the formula they give you, and that will be your general term.
Sure.
Mhm.
Do you have to simplify the general term?
No, you don't. Yeah.
You can just like write it.
Mhm. Yeah, I think this is fine. Yeah. Okay, so a few minutes remaining. If you have time, hopefully you can kind of continue to chip away at the FRQs, or you can begin working through packet 6. But I know a lot of students will be out next week, so I'm just going to pick out problems from those respective pages and just kind of going through that pacing schedule. So you guys can turn in your packets 5 and 6 at any time. Ideally, you can finish both of them by next Friday, but there's no penalty if you need a bit more time to finish both packets. All right, come get your phones.